next NASA Kennedy person, I'm up. So I'm going to go through Prime 1, and there's a wonderful video that Space Tech put out, and I'm going to actually ask our IT guy to start with that before we get too far in. I just want to say Prime's going to fly before Viper. It has two of the same instruments. It's a static version of those two instruments on the edge of the lander, so you'll get some of that information as we walk through the video. So I'm going to start there, and then I'll talk a little bit about the instruments.
NASA's first polar resources ice mining experiment, also known as Prime 1, will robotically look for ice and other resources below the lunar surface. Thanks to data from spacecraft orbiting the moon, scientists believe that the polar regions contain water ice in the form of ice just below the surface. With the right technologies, that ice is a game-changing resource that can be mined and used to produce propellant and breathable oxygen for future explorers. Under NASA's Commercial Lunar Payload Services Initiative, the agency selected intuitive machines to fly and land Prime 1 on the moon's south pole. Prime 1 will land near the Shackleton crater to drill into the lunar soil in an area that could contain water ice. Prime 1 is made up of two instruments, Trident, the regolith and ice drill for exploring new terrain, and M-SOLO, the mass spectrometer observing lunar operations. Trident will drill up to 3 feet into the lunar surface, extract lunar soil, and bring it up to the surface. Trident drills to its maximum depth in multiple phases, stopping at different increments. As it reaches each desired depth, it will pause and retract the drill string to deposit lunar soil on the surface for analysis. This is where M-SOLO comes in. M-SOLO is a commercial off-the-shelf mass spectrometer modified for spaceflight. It will evaluate the chemical elements and compounds released from the lunar soil for water and other chemical compounds. Trident will then proceed to the next specified depth and repeat the process until samples at all desired depths have been analyzed for water. If no ice is found where Prime 1 lands, NASA will still collect valuable information about drilling into the lunar soil for a future mission. NASA's Viper, the Volatiles Investigating Polar Exploration rover, will use Prime 1 technology on a mobile robot that will navigate the moon's south pole searching for additional resources. Prime 1 data will help NASA assess lunar resources to inform future Artemis missions and a robust human presence on the moon.
You know, they say pictures tell 1,000 words, so I thought that graphic was quite informative. So if you go back to the PowerPoint presentation, and we'll start from there. So when I put the proposal in for Prime, the CLIPS program was just starting up. They went ahead and did a proposal RFP out, and it was selected by Intuitive Machines. But before that, we wrote the requirements section for it. Oh, I have to go through them, sorry. As soon as I get it, there we go. We had to write the requirements that were included in the proposal. So, you know, basically I said, we need to land in the South Pole where there's water. We have potential to find water. We need to be able to sample at least down to 1 meter depth and analyze that regolith that we bring to the surface for volatiles. And those were our mission level 1, and then those would decompose into level 2s and 3s. STMD, and we agreed upon some key performance parameters, which were defined how this technology affects you know, its performance and how we would affect the ISRU community with that. So we have basically 3 KPPs, and that tells us that we have to have the ability to sample at least 5 times over the meter depth. We could get with Monte Carlo simulation. If we did 3, we could get some statistical data, but 5 is our minimum success of getting 5 different discrete samples over 1 meter. That we needed to be able to sample for at least water and hydrogen, and that we'd like to be able to sample up to the 70 AMU mass range, and that we had the sensitivity of the mass spec to be able to evaluate at least 2% water, and with the goal of being able to, the lower end being able to sample down to 1% water. So those were KPPs were derived and became the requirements for the instrument and both the Trident drill and the mass spec. So before you is the actual hardware. So spoiler alert, this is actually going to launch this year. It's on Intuitive Machines' second launch. I see Tim Crane's here with us, so we're both really excited. But it's supposed to launch sometime in a 3-month window. So between November, December, or January. And that's what our target is for this year. This is the actual hardware in Intuitive Machines facility. It's the Trident drill. The mass spec that's on there is just a 3D printed. We kept it clean. So for original, we were actually testing the camera here to make sure we had good visualization and after the install. So we went ahead and installed the 3D printed model of the mass spec. Just to remind you that the Trident drill is a percussive augering drill with a 1 meter depth. We bring up those samples in 8 to 10 centimeter sections. The cool science that we get geotechnical science data is actually, I think Janine highlighted the IMU and the sounding that we could do as well. We did query whether the IMU might still be available on the lander at that time, but that's still up in the air. We may not be able to do that. Still up for debate, but the other science that we get is all related to the functioning of the drill. So the amount of force that we push down the foot pad, we can actually visually see that with the Intuitive Machines camera. And we have little markings on the foot pad to tell us how deep it's sunk into the surface. That would provide some of those scientific measurements on force, the force on bit or the bearing on the surface, which will all inform Artemis geotechnical decisions about where to put habitat or how hard it is to mine. One of the unique things about the drill is it does have a temperature sensor at the very tip of it. And when we're done with all of the 1 meter depth, we're going to lower that drill back down into the hole and let it sit for a long time and equilibrate with the subsurface temperature. So that'll be our first in situ surface temperature measurement where we can take those measurements while it's drilling, but we really want to get a real true measurement and let it sit down there and come to the temperature of the soil undisturbed. So that'll happen towards the end of the mission. There's some engineering statistics up there, but the drill weighs about 22 kilos for the mechanical part of it and about 7 for the avionics and the harness. And so moving on to the mass spec, you heard the name M Solo. We're all Star Wars fans, so that's where the name came from. But M Solo, we actually were building 4 at the same time because we had 2 other mass specs that were originally manifested on Astrobotics' first mission and on Masten Space Systems. And we had to remove the one from Astrobotics before flight due to some mass constraints. And so it never flew. And then we had another one that was going to be on Masten, and it has not been remanifested. Those are built already mass specs. They're sitting in a box ready to fly. So come talk to Janine and I if you're interested in a mass spec. No sales pitch there. Anyway, let me tell you about the mass spec. She mentioned some of it. It is a commercially available mass spec. It's made by Infocon. We took a lot of the historical functionality of that instrument and didn't want to mess with it because it's one of the great things about working with COTS. It's already been tried and true and tested and doing very well, but avionics can be a problem. So we had to redo some of the avionics boards on it to make it ruggedized for space. It didn't come with a calibration gas system. We had to design one of those to put on it. It didn't have thermal straps. It used to have an air fan blow across it, so that was not going to work. It also hooked up to a laptop, Windows laptop, so it now speaks RS-422. So all those cool things plus a computer. It didn't come with its own computer. We were expecting that laptop, so we used the National Space Foundation or National Science Foundation SHREC Consortium and built a computer using their basic design. So those are some of the upgrades. That instrument without a bracket or attachment weighs 4.7 kilos. And you'll see it depicted on your left in its final flight form. The instrument comes with 2 different types of sensors. You can have an open ion source or a crossbeam. We chose the crossbeam based on testing we did at the Glenn Research Center because it has directional sensitivity. Directional sensitivity being very important for us as we're trying to look at a pile of dirt and we don't want everything that's coming off the lander. So hopefully that helps us when we're on the surface to some degree, and at least the timing will help us as well, knowing when the samples were taken. And again, Intuitive Machines is providing the camera images of the drill pile as it's produced. And this is what we see when we're up at Glen, and we did this in a thermal TVAC chamber. You can see the piles being created over time, reading left to right in the upper and lower rows. That's how the pile gets deposited. And you can see in the far left, the image of the field of view of the Intuitive Machines camera as it's taking an image of that. We get that image once every minute. So we can see if there's any pile collapse or change in the pile. We actually use that image to help us calculate the surface area of the pile. We're using machine learning algorithms from the software team to do that. When we look at the mass spec, one big difference between Prime and Viper and the M-Solo analysis is the time. In this particular Prime 1, we have about an hour and a half of available time to look at that decay of the signal over time, whereas Viper will have 5 minutes. So our per 10 centimeter byte. So our data will help inform Viper and that team as to whether they can just use the peak intensity of the signal or if they need to wait some time to get area under the curve. There is a strong correlation between the surface area that's created by the pile and the mass flux coming off that pile. You can see that in some of the data here that aligns that the surface area and the intensity of the signal is directly correlated to the surface area of the cone, which kind of makes sense. You know, the bigger the surface area, the more the mass that comes off the cone. And I just want to finish today with a kind of a, if I can do this, can you, I don't know if I have the ability. Yeah, can you just play that? And Angela Stickle is here actually, and she did that lighting imagery. I think, you know, when we look at these attempts to land in the lunar South Pole, this will be the first mission that's truly in right latitude South Pole. It's up in right along Shackleton Ridge. Jeff Lieberg gave me that fully lit mosaic there along Shackleton. I think I can point right in here. That's the ridge that connects Durgalash and Shackleton craters. But you can see how the lighting really changes across the entire year. And our spot is right in that, along there. So looking for exciting mission, very informative to future ISRU activities, Viper mission, others landing with Nova C, second attempt with Intuitive Machines on a Falcon 9. And our payload operations are roughly 72 hours of total time. So with that, I look forward to questions. I am going to be here all week if you have interest in talking mass spec. So is Jeannie. Thank you.
Very good. Thank you, Jackie. Wait. We have time for a couple of questions, so go ahead.
Good. Oh, okay, darn.
Sorry, go ahead.
Hi, I saw in the video you mentioned about it sampling at 5 depths. Are these going to be like equally spaced, or do you have any ideas of what these depths might be for like nominal operations?
I'm very sorry, but
Could you repeat louder?
Oh, sorry. Do you have any idea of what the 5 depths might be? Are they going to be equally spaced or otherwise?
the depth of the samples are intended to be every 10 centimeters. So we'll go down 10, deposit a sample, down 10, deposit a sample. So you go 10, 20, 30, 40, 50, that side.
Thank you.
Yeah, you're welcome.
So you mentioned about the pile formed as you're digging up the regolith, right? So each time, will you also be able to measure something like the angle of repose? So the angle that it's making each time is depositing that?
Correct. We will get the images once every minute is what's in the contract with Intuitive Machines. So that angle of repose will be measured off of the imagery.
Thank you.
Yes.
Yeah, I have one more. Nobody has a question. I have one more question maybe for you and the previous speaker. Could you tell us about how did you define the depth of 1 meter as the appropriate depth for investigating the subsurface?
Yeah, that's a good question. You want to know what was why we're all interested in depth. And it's actually, it was formed a long time ago, but the answer kind of what Janine alluded to. The reason we chose 1 meter is it was determined that was the most feasible accessible region that we could get for mining. If you went more than 1 meter deep, it wouldn't be as sustainable economically or apply across what the energy required to get down below a meter. So there was a bunch of research that was done along that. And then more recently, it's come up with the modeling by the science team that suggests that you're actually going to find the resources within the upper 85 centimeters. So that was it looks like the economics are favorable as far as a return on investment. And that was done a long time ago, you know, back in the, I don't know, Jerry Sanders, you know, way time ago, 15 or so years, they did an estimate on what the depth would be. But then the latest science data, as we get better informed on thermal models, suggests it's going to be in the upper 85 centimeters anyway. So that's cool. It's good they worked out. Thank you very much.
Thank you very much, Jackie.